pretty much everything. So thank you, welcome back. We are going to be doing a one-off today. It's like most of my lectures, it's going to be a tutorial session in which I'm going to talk about some of the tools that you've, mostly about debugging today, but I am going to mention some of the tools that you've been exposed to because of course most of these tools, as I'll mention later, are entire topics in and of themselves. In fact, doing DevOps, which is development operations, where you are just writing build scripts and deployment scripts all the time, that's an entire full-time job. In fact, at the last place that I worked at, there was 2 people whose full-time job it was just to write and maintain deployment scripts. So these are big topics, and this is, and I'm only, I take the opportunity in Computer Science 1 to expose you to these topics and these tools, but of course we don't have the luxury of diving into them, much deeply. But of course, from day 1, we gave you an exposure to source control and versioning using Git, of course. Now, Git is, Git is rather mature. I think it's about 10 or 15 years old. I forget when it was born. But it was created by Linus Torvalds. And it was certainly not the first version control system. You had these ancient ones, CVS and SVN, which have basically pretty much been replaced by Git. But Git is a tool in and of itself. Again, another student organization, we were talking about student organization before we started broadcasting. Another excellent student organization that you can be involved with is OS2G. And just last Friday, I tried to promote it. Last Friday, they had a virtual Git session. Somebody is always doing a Git session, whether or not it's Initialize or OS2G or something like that, pretty much every year or every semester. Hopefully, this is a tool that you start using on a daily basis, even just to keep track of your own code. Make sure, of course, you're not putting any private code into. Let me refresh this. Still only see one. Okay, so there are people watching. All right, good. But anyway, so where was I? Sorry about that. It's an extremely useful tool, and just for backups, but also for tracking code that you introduce a bug. Well, you can go back to a previous version or something where that bug didn't exist, and then you can track down differences. You've also been exposed to build systems, right? Make, CMake, or what did you try? What were you using yesterday if you did the Java version? Do you remember? Did anybody do the Java version? Nope. All right, Ant, right? Yeah, there we go. That was for Java, of course. Now, these are all cross-platform. In fact, these are languages, basically, unto themselves. But the whole point of using something like this, and I'm going to use the one from the Lab 6, the C version of Lab 6. This is by no means a complicated project, but still, there were about a dozen or so files, right? And of course, if you had to compile this manually every single time, you're sitting there, type. Why do that when you've got when you can create, put that into a script file basically, and then repeat that. That's what this make file does. Make is basically a language unto itself. You've got variables here, so that if you ever wanted to change which compiler you want to go from GCC to Clang or something like that, you only have to change it in one place. And every time that you use this variable, of course, it's changed for you, right? You've got flag variables. I want to turn on all of the warnings. Or I want to speed up the build process, and I'll come up here and change this so that it goes away, and I don't have to worry about that anymore. You can have conditional builds. So, okay, well, let's detect what system we're on. We're on a Mac, or we're on Windows, or we're on SUSE Linux. Okay, well, we can compile in a different way. Bring in that file that's compatible with that operating system instead of that file for that operating system. It's extremely powerful. Not only that, but it provides dependencies. For example, image driver. How do you build image driver? Well, the rule to build image driver depends on these 3 files. So this is an object file, this is an object file, and this is a .c file. So make automatically says, okay, well, this file exists, it's just a source file. This file doesn't exist. How do I build it? Okay, well, there's another rule for building that, and it's dependent on these 2 files. And okay, I've got that header file, I've got that source file. How do I compile them? Here's the rule for compiling them. Once that's done, then it comes back up here and says, okay, how do I compile this one? Well, I compile it this way, and now I'm ready to compile this, right? So all these rules can be defined, and this is extremely simple example here. You can get extremely complicated if you've got thousands upon thousands of source files that you want to compile for 50 different operating systems. Of course, you can create a big giant make file for this. That becomes a job unto itself, right? That becomes a project unto itself almost. So make, of course, simplifies that so that at the end of the day, when you actually want to build it, you just type make and that's it, done. Not only that, but you've got also dependency management. You've got, that's just how to, that's a very simple example of how to build. But you also have, say, deployment scripts. Right? That once you've built your executable, you need to push it out to a web server because it's a web application or something like that. Or you need to push out the updates to the updating system so that it gets pushed out to all the Windows systems that are registered with your software so that everybody can get updates automatically. Right? It's an extremely complicated process if you've got a complex program. So you've got deployment scripts. You also have dependency management. Now, this has dependency management in that this file is dependent on these 3 files, and then transitively, this file is dependent on these 2 files. But what I mean by dependency management is if you start bringing in external libraries, like say CMaka, then you need to be able to have a way of managing all those dependencies. This project requires this library over here. Okay, well, I can script that to say there's a dependency on this, and it'll go out and automatically download it and make sure that it's there. By the way, that library depends on those 3 libraries over there. And that first of the 3 libraries depends on that library over there. It takes care of all that complex web hierarchy of dependencies for you. Now, I don't know what the standard is for C, but of course, the standard for Java is Maven. Right? And there's even a website called Maven Central where all of these libraries, all of these recognized libraries are organized. Most programming languages, most development ecosystems will have some sort of a dependency management. For JavaScript, you've got NPM, which is Node Package Manager. That's actually just for Node, but it's the same idea. Right? You don't want to have to, when something becomes sufficiently complex, you start to lose the forest for the trees, and you need a tool to manage all that stuff. Right? This all falls under DevOps. Right? Development operations. And again, that's an entire job unto itself. It's not exactly system administration. That's an entirely different thing too. It's kind of halfway between development and IT basically, where you are actively writing scripts all the time, writing and maintaining scripts all the time. I've also exposed you to unit testing, right? Both in an ad hoc manner, right, where you sit there and you type and you try to run your program. Okay, my program works, at least for this one test case that I tried. That was an ad hoc, right? It's not very formal. We then moved on to informal testing, right? And then formal testing, right? Informal would just be you rolling your own code saying, test this function and then have an if-else condition. If it passes, then great, increment a counter. If it doesn't, then false, decrement or increment the number of wrong calculator, right, or counter. But you also have more formal testing frameworks. For C, we exposed you to CMaka, right? And for Java, of course, the default is JUnit. You might have to think way back to the first assignment, the Capricar project. We only gave you exposure to it. We wrote it for you. We didn't require you to write anything. Again, a lot of this stuff goes beyond the scope of this course. We keep it on the periphery so that you know and you're aware about it, but we're not going to make it the focus because, again, the focus is the basics, learning how to program to begin with. All right? You also have exposure to static analysis tools. Right? And for this, I'm going to actually show you a little bit more today. Right? For example, with C, you could use GCC as a linter. Remember the WAL flag? I helped somebody out in the online office hours the other day where He pulled up his code, and I immediately saw the problem. And I said, well, wait, let's go ahead and compile with the WAL flag. He did that, and he immediately then saw the problem, right? And then he said, he'd been spending 20, 30 minutes on this one problem. If you'd run it the linter, you would have been able to see it immediately, because a computer is smart, right? Well, computers are dumb, but if you program such that you're looking for those common errors, then use those tools. Another opportunity here, it would be GCC WAL W extra, right? So it's counterintuitive, but if you turn on all the warnings, that's apparently not all of them. There are some extra warnings that you might want to turn on as well. Don't ask me why. Extra should be a few extra, and then all should be all of them, period, right? This one should subsume this one, but I think that there are instances where it doesn't. For example, let's take a look at this array program that we're going to be using for demonstration purposes. I've got a lot of bad code in here, intentionally bad code in here, right? You might be able to see it immediately, what's going on, what's wrong with it, but if you don't, then you can always, use WAL and W extra to come up with warning after warning after warning. One, two, 3, 4, 5 warnings here, right? You're not returning anything from a function that expects to be returned from. This variable x is set but never used. The initialization from a pointer, that doesn't look like right at all, right? Wait, you've got 2 placeholders here, but you've only got one thing that you're printing, right? All these things can come up if you're using proper static analysis tools that, that tell you exactly what's wrong or give you a hint at what might be wrong. Clang, or Clang, is another compiler, an alternative to GCC, and you can turn on all of its warnings by using analyze foo.c, right? So when you're compiling, you can compile it with this analyze flag, and it's available on CS50 and on the CSCE server. When I do use Clang here and analyze array program.c, I don't get the same number of variable warnings, and I don't get different, but I do get some different warnings here, right? The value x stored is never used. That's similar. There, the left expression of this is an uninitialized variable. Remember, uninitialized variables in C have no default value, so it could be garbage. Garbage plus 1 is still garbage. Clang is now warning you about that. So you might get a potential memory leak of the array here, right? So as you were using Valgrind yesterday, which is a dynamic analysis tool, you could also use Clang here as a static analysis tool to potentially come up with, there's something fishy over there. Remember, it's lint. It's not errors, it's lint. It's stuff that looks dirty. Oh, no, that's fine. That's not a piece of lint. That's part of my shirt, right? But turning these things on and then checking them out to see, is it actually a problem? By using these tools, you'll be able to understand that. Yeah?
So like how can it tell the potential for
It's probably just using some rules. It probably saw malloc, or it saw a pointer and maybe a memory allocation, but this is in a different function that you didn't see. So it saw malloc, but it never saw free. And so it's thinking, and then you never returned it, so fishy, that's probably a memory leak, right? But you can come up with now, these things will never be able to come up with all of the problems. If they could come up with the problems, then they could automatically fix them too, right? And we wouldn't have to read the output of a linter. We still have a human factor with all this stuff. We're not there yet. We're not to the Star Trek computer that can program itself, right? You also have access to Facebook, Books Infer. And to run that, it's actually a 2-step process. You basically have to capture all this information about a program, and then later on, there you go, later on you can analyze it. So let me go ahead and do that now with this buggy program over here. Infer capture, GCC array. So this is infer capture, and then this is just a delimiter here. This is actually what we're going to be, it's going to compile, and during the compilation process, infer is going to monitor the compilation process and see how it works so that it can find potential issues here, right? And then later on, you can go infer, analyze. Analyze that build, right? All right, took almost a second here, and after it's finished, it'll produce a report right here. Lots of issues with this program, right? Uninitialized value, dead store, I'm not sure what that means. The value, that X is used, but it's never actually, you never actually do anything. Yeah, you set it, but you never actually do anything with it. Are you sure that you need that variable? You've got a potential memory leak here. It called malloc, you're asking before, it called malloc, but there's no, but that memory is no longer reachable after that line. So that's one of the rules it uses to determine. Null dereference, remember Bret Hart, hitting you over the head with a null pointer dereferencing. Memory leak, null dereference, etc. So I found 2 potential memory leaks. This is not definite. These are potential memory leaks. 2 null pointer dereferences, an uninitialized value, and dead store. That's just the tip of the iceberg of what this tool can do, and all these tools can do. Yeah?
So like, to what extent does this actually like use affiliates with Facebook?
Facebook developed it. So the question was, what's the affiliation with Facebook? Facebook developed it and then released it to the community so that other people could use it. Facebook does a lot of stuff like that. For example, I think that they've got a PHP compiler. Typically, PHP is an interpreted language, but of course, interpreted languages are slow. So what they did, but Facebook began in PHP. It's still in PHP. And what they did was they developed a just-in-time compiler, or maybe it's a full compiler, I'm not sure, that compiles PHP code to actual machine code so that it can run faster, right? Because you've got so many users, you've got to have, the efficiency becomes a huge issue there. I forget what their compiler is called, but they've got a whole bunch of other tools that they release to the community. Most companies do this. Google has a lot of tools that they release. Apple, they developed an entire language and then released it to everybody Swift. And the extent to which, I mean, it's not altruism. They want people to use their stuff because they want people to be, lock them into their stuff, which they actually then start charging for. But of course, this is, I don't think that Facebook Infer is free and open source. It might be, but it's definitely free, as in beer, if you've ever heard that term before. Free as in freedom versus free as in beer. So free as in beer means free of no charge, right? Hey, free beer, here you go. No charge for this beer. It's on me, right? They're giving it away for free. But it's not free as in freedom because they're giving it to you, but there are potential strings attached. They can always take it back. They can always, tomorrow Facebook could say, okay, we're no longer going to support this, and you have to stop using it, and whatever, right? Because they still own the rights to it, the copyrights to it. Right? Free as in freedom is somebody who releases something that is a public domain or under a GPL license or something like that, where everybody is free to use it and even make money off of it themselves if they want, right? In some cases. Not dynamic programming language. Trying to type and think and talk at the same time. Dynamic analysis tools. All right. Actually, before I do that, more. All right. All of these are listed in one of the documents available on the GitHub page, and I'll take you there now. So it's a troubleshooting guide. Now that we are in the 7th week, we're pretty much beyond the basic Hello World program. Once you get to a certain level of complexity, now these tools start to become useful. If we started introducing these tools on day 1, there's nothing to debug in a Hello World program. There's nothing to analyze in a Hello World program. So you need a little bit of, you need a sufficient level of complexity to start talking about these tools, to actually start seeing their use, the usefulness and the utility of them. But I have put them into, there's another one called Scan Build. There's Facebook's Infer. There's a whole bunch of static analysis tools here that I mentioned. And of course, Valgrind that you used yesterday, if you did the C version, that can be used to check for memory leaks. And I'm going to do that now. Not A dot, yeah, A dot out, right? So segmentation fault, and there was a bunch of memory leaking, right? Actually, let's open it up. I think I commented it out. So let's open that up and make sure that it's actually there. Memory leak. There we go. It can be used to find other issues besides just memory leaks. So let me go ahead and run valgrind here. First of all, I have to recompile it, of course, because I've made changes to it. All right, good. I should take care of those, of course, before proceeding, because it'll probably catch a lot of the stuff that I've already, that valgrind is about to tell me about. It's intentionally wasting some space, like you did yesterday in your lab, right? Your lab, you wasted about 40 million bytes, right? So here, too, we have memory leaks, right? But we also have other issues. Down here are the memory leaks here. This is exactly what you did yesterday. There were 36 million bytes, and then another 4 million bytes that were potentially lost, right? But this can be used to detect so many more other types of problems. For example, an invalid write of size 4 bytes. I did an illegal operation somewhere, which would have eventually caused a segmentation fault in an actual real run of this program. But in valgrind, it detected it and moved on and reported it to me. Where did it happen? Let's give myself some more room here. It happened somewhere in this file. Where? Well, it happened at this memory location. Is that at all useful to you as humans? No. So let's go back and compile with another flag here. This is the G flag. The G flag preserves the function names, the line numbers, the variable names, and everything else that you put into a program. Generally, those are wiped away because those are intended for a human audience. Generally, those are taken out, and who cares that you named your variable foo versus a variable named bar? There's just a variable, so it uses some internal designation instead of the human readable stuff. The G flag preserves all that stuff so that when you run valgrind and eventually GDB today, I'm intentionally waiting a second after each one of these so you can actually see it, so we have to wait 10 seconds here. There we go. Now when I look up at this report, oh, hey, guess what? Where did it happen? At line 62, at line 58, at line 64. So those lines are sus, right? Let's go ahead and, suspect, let's go ahead and check it out. For those not playing the Among Us game, right? Yeah, there we go. Let's check it out. 58, I think it was. Line 58. There's line 58. So we allocated 400 bytes. That was the message that we got. And then something happened on line 62. What happened? We tried to access an index. What was that index? -1. Is that a valid index? Nope, we went out of bounds. What happened on line 64? We tried to access an out-of-bounds index the other direction, after it, right? And that's exactly what the message was. Let's see, where is the message here? Invalid write of size 4, before a block right there, and after a block happened, right? So you got to be, I mean, you can use this tool to detect not only memory leaks, but illegal accesses. So if you're seg faulting out, what's going on? Why is it seg faulting out? You can run valgrind and it'll try to tell you what the issue is, right? But that's called a dynamic tool. It's called a dynamic analysis tool. Why? Oops, that's not what I wanted. Because the difference between dynamic and static is done before compiling. It's looking at your static code. Dynamic, when a program actually runs, lots of moving parts. That's why it's dynamic. It's actually analyzing the program as it runs, right? And so you have static analysis tools, you have dynamic analysis tools. Another dynamic analysis tool that you have is a perf tester, or performance testing, right? And these tools are generally called profilers. The profiler simply runs your program and says, you've got a program that's now correct. There are no memory leaks. There are no issues with it from the perspective of being correct, but it's just taking forever, right? It is really inefficient. What's taking so long, right? You can run this through a profiler, and you can produce what's called a heat map. That 90% of your time is spent in this function. Well, that's where you focus your efforts. What's going on in that function that is so inefficient? Well, maybe it's not that inefficient, but maybe we can restructure that function to use a different algorithm that is much faster algorithm. Okay, now the perf tester says now only 5% of your time is spent in that function, right? And the one that we'll use later on, I'll demo it later on because we're not there yet, is gprof, which stands for the GNU profiler. These things are not named with anything clever, by the way, right? Debuggers. That's the one that I want to focus on for the rest of our time today, though. So what is debugging? Well, debugging is simply, you've got an error in your program, you've got a problem in your program, and you want to fix it. You want to know where is the bug, right? First of all, you have to identify the bug, right? Meaning that you have to identify input that causes the bug, right? You need to do this to make the bug reproducible, right? And I get this all the time as an instructor. It works on my machine. Well, it doesn't work on that machine. That still means it has a bug. You need to be able to reproduce that error in order to finally, zone in down on that error. And usually it works on my machine because I tried this one test case, and of course it passes because it was an easy test case. But guess what? We're running it on 10,000 test cases and corner cases that you may not have thought about and not tested, like, for example, checking for null pointers, etc. And so being able to reproduce that error by finding an input that causes the error, that's your starting point. Because then you can run it through a debugger to find out what's going on, right? Do not, are we good on, is anybody here streaming? Is it good?
It's kind of stuck in a low thing.
Yeah, it's kicked down to like 1K. It's encoding overload. Come on, man.
Would you recommend a streaming software you use?
OBS, it's open broadcast software.
Yeah.
Looks like it's good, it's better now. But I've had an issue. I've had intermittent issues with my Mac simply because I think it's from 2015.
Yeah.
And wow. And I'm at 6%, but it says that we're on we're on power. So that's probably the issue. It's not for some reason I'm not being powered. And so it's trying to throttle my processor, and that's why it was starving. There we go. Oh, okay. Hopefully that takes care of it. I'm not seeing an issue anymore, but let me know if you do see an issue.
The image is still kind of sticking, but I can check the audio too real quick.
Okay, good. But anyway, I'm going to okay. Okay, thank you. We were just checking on the audio for those at home. In any case, I wanted to, I'm just going to go in, get into it and start demonstrating how to use these things. So first of all, we'll go ahead and look at GDB, right? Using printf statements is not a solution. You need to make sure that you are using a proper debugger. And a debugger is basically something that allows you to simulate a program, stop a program's execution so that you can actually look at stuff, because most programs are just ephemeral. They're really, really quick. They die really, really quick. Like a segmentation fault will happen, and what happened, right? Well, we need to go a few lines before the segmentation fault happened to see what actually happens. Not only that, but there are situations in which you can have undefined behavior on line 5, and it won't manifest itself as a segmentation fault until line 100. right? In which case you need to be able to, a printf statement would be completely useless by then, because you need to, you profile it, you need to actually jump into the code to see what's wrong. So again, you need to use the -g flag in order to preserve the function names and the line numbers. Otherwise, you won't be able to look at your code while it is executing. We'll go ahead and go with arrayprogram.c here. And I'm already getting a warning here. But GDB, the resulting executable is called a.out. So I'll open it up with GDB and make sure that it's all visible over here. There we go. And GDB is what's called a TUI, text-based text user interface. So of course you're going to have to type out commands. The first command that you'll probably want to type out is, well, run, right? And wasted some space, wasted some space, wasted some space, or something like that. And that'll, but it's not really helping me because, well, it's running normally, right? So there, it stops, and at least I can see what happened on line 26, but I can't see the rest of my program. So I'll go ahead and go out with layout next. Right? And now I can see my entire program. It's paused right here on line 26 because we had a segmentation fault. And you can see why we had a segmentation fault. I'm making my pointer point to memory location 7 instead of properly creating a block of memory for this. But I can go ahead and scroll through. Right? I can actually, very powerfully, look at the assembly code. I can look at the assembly code along with the actual code. I can look at the machine code and the actual code. And I'm just going to go ahead and go back to the original here. Because, of course, that's what's intended for humans. All right, well, I don't know what happened on line 26. I need to stop before that. So instead of waiting for a problem to happen, what I can do is I can set what's called a breakpoint. I will break at main. I'll break at line 25. So you can set breakpoints based on function names, or you can set breakpoints based on line numbers. Right? And you can see right here, there's a B plus and a B plus. That's because that's where it will break. Now, I've already run this program, so I need to start it from the beginning. All you have to do is type run again and say yes. Right? Yeah, go ahead. Break is you're breaking out of something. You break out of the execution. Pause, basically. It's not a good name. I agree. It should be pause, right? But it's a breakpoint. It'll break the program execution at that point so that you can stop and look what's going on here, right? And every so often it'll screw up. You see these 2 for loops here. Well, obviously there were not 2 for loops. Every so often it'll screw up with the display. You can always hit refresh, and it'll redraw the screen for you. And you can move up and down. Okay, now I've got a break here, capital B now, and I can actually walk through this line by line by going next, right? Next, next, right? And refresh every so often if you need it. That goes line by line by line. Of course, it gets tedious to type next, so you can just go N. Or you can go enter, right? Enter, oh, wait. That was a function, right? It's going to execute that entire function before going to the next line. Refresh. Now it's at the next line. I wanted to see what happened in that function. All right, so let's go ahead and run again. Refresh. Now next, 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 next. Refresh. I'm about to go in this function. If I hit next, it's just going to go in the function, execute the entire function, and then go on to the next line. Next only goes to the next line. If I want to actually go into the function, I need to step into the function. And when I do that, now I'm actually in the function, and now I can go ahead and go next, next, or just enter, 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 enter. Right? Refresh. Okay? So step, next. Those are 2 basic commands. Oh, what iteration am I on? I already went through 1 iteration, so I should be 2 by now, right? Print I. Oh, I'm still on the first iteration. But if I go next, print I, now it's 1. So if you want to take a look at variables, don't do printf statements. Load up a debugger, set a breakpoint, get to that point, and then you can print out all of the values. For example, print array, right? It's null right now. Why? Because, well, it was just declared. It redeclares it on each iteration of the for loop because it's scoped to that for loop. So let me go ahead and go next here. And now print array. All right, now it's a valid memory location. This is a null pointer memory location, by the way. Okay, next. Next. Did those values take? Was 42 actually assigned to that? Array of 0. Yep, good. Print. Well, what's in that second one? 0. Print. What's in that other one? What's in the first 10? Do you see what I did there? It is an array, so I need to dereference it. Well, how many things do you want to print out, or how big is the array? Well, we know that it's 1 million, so I'm not going to print out 1 million things. I limited it to 10 here, right? So you can print variables. You can print variables in an array. You can print out an entire array, right, by using this syntax, okay? What else? Oh, to set a, so let's go ahead and run this from the top again. Refresh. No, I didn't mean to stop. I no longer want to stop at line 25. So you can clear a breakpoint, clear line 25, and delete a breakpoint, refresh it. You can see that, oops, why is it not gone? Clear all. No, clear main. There we go. Refresh. There. Now they in fact are cleared. Yeah.
So you mentioned like the one breakpoint, line 25 was like capital B.
That's when it stops, right? So break line 25. Now, I would have to go next to get down to line 25, or I can type continue, and it'll resume the program up until the next breakpoint. Of course, it's calling that memory leak function. I should just get rid of that, but because it's wasting 10 seconds. And there we go. Refresh. There, now I'm at line 25. So if you don't have to, if you want to resume the program, you can type continue. You can type next, and of course now we get a segmentation fault. Why? Because primes here is 7. It's not it wasn't properly initialized. So let's go ahead and quit out of this, and let's get rid of some of these issues. First of all, I'll get rid of the memory leak by simply not doing it. I'll get rid of the out of bounds test by simply not doing it. And let's go ahead and call malloc properly here. Malloc on n times size of int. Actually, n. Intentional mistake here. Right. Actually, no, we're short on time, so I'll just go ahead and do this. There we go. Now, is this going to work? It will work, but how many, you want the first 7 primes? N only needs to be 7, but what value does it have? 77. So that's another bug. It's not really a bug, but it's just a time waster, right? But there's also a bug up here, right? If I run this just raw, right? Then argument, here I'm trying to print out all the arguments, right? A.out, A, B, C, D. Right? It should print out A, B, C, D, but it doesn't. It prints out all this garbage. What's going on here? GCC, GDB, and layout next. Run. Actually break main, then run. Right? Refresh. So next. Oh, well, it gets out of that for loop almost immediately. Why? When I ran it from the command line, I provided those A, B, C, D command line arguments. I'm running it through a debugger. How do I do the same thing? Set args to be A, B, C, D. And now let's rerun the program from the top. Yes, refresh. Let me show you that it actually is there. If I if I print argc, it should be, if I provided A, B, C, D, and on also the the executable file name, 5, good. Print argv sub, and how many of them are there? 5. There they are. There's the command. There's the executable file name A, B, C, and D. That's what I would expect it to print. But when it doesn't, right, it prints that. Why? What was the issue? I have two placeholders here, and I should have two things that I want to print. And not only that, but the second one that I'm printing here, I'm always printing the first, right? So even just, focusing on one line will help you to identify a bug, right? Quit. Let's fix it. And by the way, there are debuggers that allow what's called hot swapping, where you don't have to quit out of the debugger. You can change the code, have it recompile, and then it doesn't always work, of course, because you're not dealing with the same program as before. So it's always just best to quit out of it and redo it anyway. Right? Yeah? Just if you want, if you need to debug with command line arguments, then you certainly need to be able to set them in order to debug, right? Right. So layout next. Break, or let's just run it and refresh. Right. So it exited normally. We don't have any issues here, but unfortunately, the output was wrong. What is it doing? Let's quit. This total is 7. Let's take a look at the code again. What are we doing here? We're calling this sum function. We have all these primes here, and the sum function just simply adds them all up, right? So the sum of the first 7 primes should be, take out your calculators or add those up really quick, 58, not 7. Yeah? That's exactly the issue there. And running a linter would have told us that. Let's run GDB, though, on this, and break at sum, and see what's wrong. Run, layout, next. Right? So let's make sure that we receive that array correctly. If we print out n, well, there's 7. If we print out array, well, of course, that's going to be a memory address. So let's print out array, dereferenced, and there are 7 things in there. Okay, that all looks good. I'm going to now go through this for loop to make sure that the sum is correct. All right, so let's print total. Right, that's 0. Okay. If I go through the first iteration, let's print out a total again. Now it should be the 2, right? Because 0 plus 2, that was the first thing that it added. The next iteration, it should be 2 plus 3, so it should be 5, right? Print n, or print total, sorry. Okay, now it's 5. That seems like tedious work. I don't want to have to go through every iteration and print every single time. Let's go ahead and set a watch on it. Let's watch the variable total. All right, next. It will automatically tell me whenever it's changed. It went from 5 to 10, right, because we added 5 now. The next iteration, it will be 7, so 10 plus 7 should be 17. Right? It goes from 10 to 17. Keep going next until, oh, that's the value that I expected, 58. But as you observed, oh, what do I do with that value? I don't actually return it. Okay, so I found my other bug. Oops. Emacs. Let's go down here and fix the sum function to return total. Also, we should be setting this to 0. So both of those are fixed now. And I do want to call this other long function here. Actually, before we do that, let's make sure that it works. You don't have to run the debugger all the time, right? If I just, oh, okay, no, it looks fixed to me now, right? Good, let's go home, right? Only when the next bug shows up do we need to then, okay, fire up the debugger again. But what I do want to do is I want to show you this long function over here. There's the long function. All it's doing is counting up to 1 billion. But when it gets to 20,000, what does it do? I divided by 20,000 minus 20,000. What's going to happen? Divide by 0 error, right? And that will manifest itself as a floating exception. All right. Now, we saw that, and we know what the bug is. But let's suppose that we didn't know what the bug was. Layout, next, run. All right, there. It happened on that line 52. We received an arithmetic exception. Right? What happened the iteration before that? So let's go ahead and set a breakpoint at long function, right, and run this again from the start All right, there. We're now at this, but it really only happened when it was 20,000. So I'm going to go ahead and 20,000. I have to do this 20,000 times in order to get to reproduce it. And by the way, when I get to 20,000, I'll miscount and go over, and I'll screw it up. So what you can do is you can set what's called a conditional breakpoint. Break at line 52 if I is equal to 19,998. That's a few iterations before the error happens. And I can run this, clear long function. Actually, no, I'll keep that. And let's run this again. So it stops first at the long function. I will continue until, that's going to take a little bit here. Now, normally, it would just go by in a flash. But we are running this through a debugger. We've got a program simulating another program. That comes with some overhead. So it's not going to be as efficient. Don't use a debugger to determine efficiency. That's what a profiler is for. So print I, and you see that it stopped at 19,998. Any C condition that you can write, you can make a conditional breakpoint. Very, very useful tool. And by the way, if you get caught in an infinite loop, you can still hit Control C to pause the program. It doesn't kill the debugger. It just pauses the program wherever it is. It's really, really great and useful. Okay. Most of this stuff I went over. There might be some stuff that I forgot, but that was the gist of it. Right? There are all of the commands that I went over, the basic commands that I went over. I only touched the tip of the iceberg. And in fact, most of these commands, I don't remember them on a daily basis because I don't use them on a daily basis. Hopefully you're not debugging on a daily basis because you're writing decent code that you're only debugging maybe once every 5 days or something like that, right? Because you wrote good, beautiful code to begin with. In fact, there are some people who take the philosophy that you should never use a debugger because I forget who said it, but the claim is you were not smart enough to avoid the bug, therefore you are not smart enough to determine what the bug is. Which I do not agree with at all, but you can kind of see a philosophical chicken and egg kind of thing there. That can you create a rock so heavy that you can't lift it, right? Can you create a bug so pernicious that you can't debug it? That's more of a philosophical question. Now, over here, I don't have the exact same program over here in Eclipse. But Eclipse has a debugger built into it. You see this little bug up here? That's the debugger, right? So what I'm going to do is if you click this, of course it'll run it, and it'll ask you to switch. You can remember that to always switch. It is a different perspective. Remember, over here you've got a GitHub or Git perspective. You've got the Java perspective, which is what I'm currently in. There's the Git perspective. Here's the debugger perspective, this little bug right there. I'm going to switch over to it. All right? And is this visible everywhere? I want to make sure that there, okay. I'll go skinny here. There we go. So you see what happened here, right? Oh, okay, maybe it didn't happen. So you can stop the execution here. You can rerun it by simply just hitting bug there. All right, something's happening here. What happened? It was an arithmetic exception. I thought I cleared all these. Nope. Okay, fine. What is going on? Why are you not? Come on. I think it hiccuped here because I let it. Okay, there we go. All right, I just had to slide. Here, I'll slide. Okay, fine. There we go. There it is. So over here, just like watch or print, it's a graphical user interface, GUI rather than TUI. So you can actually look at each one of these variables and see, well, that A is set to 10, B is set to 3.5, etc. Right? And over here we've got main is throwing an arithmetic exception division by 0 error. Well, obviously because I'm dividing by 0. Right? I can step through this program. Oh, okay, I want to know what happened right before that. So I can set a breakpoint here by double-clicking. That little blue thing right there is a breakpoint. I'll go ahead and stop and start the program again, and you see that it stops at that breakpoint. How do I go next? How do I step? Those are the buttons up here. This is step over, which is next. This is step into. So step over is what I want. I want to go next, next. If I had a function call, I of course would step into that function. You can resume, you can stop, right? All these little graphics that are self-explanatory because, well, nobody has a tape decks anymore, right? But these icons come from the 80s and tape decks, right? The stop button, the play button, they're still used even though you don't have those buttons anymore. You have them now graphically on your on Spotify or Pandora, but it's because they come from the old cassette players, right? Maybe even before that, like record players and stuff. I'm not sure. Yeah. Exactly, the phone icon, and whether or not anybody actually has a landline anymore, especially like the old style, big giant receivers. That's questionable. Well, all you have to do is go down to. Well, I'm sure that you're right out of high school. I'm sure that the high school had that kind of stuff because they never get rid of anything that's potentially useful. Right? So I'll go ahead and stop this, and of course I don't need this anymore. So yeah, arithmetic exception. But what happens when, or let me go ahead and run this again. All right, there we go. We have a null pointer exception. Well, the null pointer exception occurred at line 16, so I can jump to that if I really want, and I could say, what was null here? Right? Well, it's pretty obvious that the only thing that could be null is S, but if you've got a very long line, and involving 5 or 6 different variables, which one of those variables is null? I have no idea. So am I going to have to set a breakpoint right before that and then simulate it up to that point? I'm not going to do that. What I'm going to do is I'm going to set a conditional breakpoint based on the type of exception here. So over here, go over to the breakpoints tab, right? And let me get rid of that. I'm just removing the breakpoint that I put up here. And what I'm going to do is I'm going to put in an exception-based breakpoint. What exception do you want to stop on? A null pointer exception. Okay. Anywhere in the program, if a null pointer exception occurs, it'll stop right before that so that you can see what exactly is null. Now let me go ahead and run this again. There, it stops at that line. What's null? Well, it's not args. It's not A, it's not B, it's not total, and in fact it is S. Oh, S must be the null pointer right there. Great. Yep, of course, it's because I assigned it to null up here. Oh, didn't mean to do that. Stop, change, keep going. Right? And by the way, you could have done it with the arithmetic exception up here as well. Let me go ahead and run this, and it went fine. Everything went fine. It doesn't actually do anything. But again, if you want to do a conditional-based breakpoint, what I'm going to do is here, I'm going to, because this is 1,000 iterations. All right. I want to stop at iteration 500. I don't want to stop at this line and then hit next 500 times. So I'm going to set a conditional breakpoint on line 14 and there we go. Go over here to breakpoints. I'm going to get rid of this null pointer exception because I don't want it anymore. And I can make this into a conditional breakpoint. You might not be able to see it because you might have a smaller screen like I do right here because of the low resolution projectors. But if you bring this up, you can see this box right here, conditional. What's your condition? If I is equal to 500. Right? Now, I'll go ahead, save that, right? Control S or Command S. And now go ahead and run the program again, and it stops on that line. Look at the variable. Guess what I is? 500. Right? So conditional breakpoints, exception-based breakpoints, regular old breakpoints, right? You can view everything. You can view all of the variables all at once that are in scope. If you highlight the variables, you can even, what if it were 20 instead? You can hot swap variable values while you're running. And does that make a difference, right? If it had the correct value, then of course the bug wouldn't be there, or the value that I expected, basically, right? All right, what if computer science is fun? What if that was a different value? Is really fun, right? And you can change these things. Well, if I do that, then I will set another breakpoint here. By the way, this is a warning. The breakpoints are going to be under that. There is a breakpoint there. Believe me. In fact, you can see it right here on line 16. I will resume because I don't want to go 500 iterations to finish out that while loop. And then I'll be down there. And I'll go one more. By the way, don't step into... okay, I'll do it. Let's step into it. Step into the split function. That split function is part of the Java library. If I step into that, now I am debugging the Java library. It's probably not something you want to do, right? So I'll stop this and go back. There we go. And go continue. There we go. And now that I'm there, I want to see what happens to this, this array right here. Does that array actually split? We haven't talked about this yet, but does this array actually split this string? If I go one more iteration, then I can see that now there's this new tokens here. I can expand it and see there's computer science is fun. Right, split along spaces. And I can change each one of those things. Right. Question?
So what happens if you accidentally mess with the Java library? Yeah, someone will mess up that bad, but I also know that my own self.
You won't be able to. I'll stop and try. First of all, you won't be able to change any of the code. You can't even do that with your own code. Here I'm mashing the keyboard, and you're not going to be able to change the code on the fly. And not only that, but this is a .class is compiled, but it has the way that I downloaded it, and the way that if you followed the instructions, downloaded the JDK, it downloads both the compiled code as well as the original source code, so that when you're developing stuff, you can take a look at, well, I'm at that line in the compiled code, what does that correspond to over here in the original, so that you can actually look at it and you can see even the Java docs here, et cetera. But you're not going to be able to, unless you modify it and then recompile everything, in which you're building your own JDK, you won't run into trouble. So don't worry about it. And I was right. My Mac was throttling me because it was not powered up. It was running. It was running off of battery until it got down to 6%, and then it started throttling my processor, and that's why it started to kill OBS. Throttled my processor because it knew that it was about to run out of power. All right. Any questions?
We won't have to do this for
Like the midterm? Well, you never have to do this if you write perfect code. You'll never have to write a debugger as long as you're perfect for the rest of your life in code. You'll only run a debugger when you need to, right? If you've got a bug and you can't figure it out, you run a debugger, fire up GDB, and at least, in fact, in the future, when at some point, I give LAs the instructions that, if there's a segmentation fault, then I have them fire up GDB to at least find out what line number it's on. And if an LA and a student find out at least what line number it's on, then usually the student finds out, oh, well, yeah, of course, now that I see the line number, I see what's wrong, it's obvious. And if they'd run their own debugger instance, then they would have been able to find that out. There's also something called rubber duck debugging. Have I mentioned that before? No? Well, you can come down here and look at my computer at some point because I put a little rubber duck sticker. I do that for a couple of reasons. I'm pointing at you right now. I do that, one, so that I remember that there is a camera right there so that I can make eye contact if necessary. But I also do it for another reason. So if you ever find yourself alone and debugging and you're racking your brains out, right? If you had somebody else there, you could try to explain it to them. This is what I've tried. This is how the bug has manifested. I'm getting a segmentation fault on line 45. This is what I've tried. This is why it didn't work. Like, if you start explaining this to some other person, and this is the secret of teaching too, you just start asking questions rather than them telling you stuff. Like, well, what happens on line 23? What happens on line 24? What happens on line 25? If you get that dialogue going, then 9 times out of 10, that individual will come to the conclusion themselves. Right? Why? Because they had to explain it. The mere act of explaining it sorted it out in their minds. And once it was sorted out in their minds, then they immediately understood what the issue was. If you don't have that person there that you can talk to, take a little rubber duck and put it at the top of your computer and start talking to the rubber duck. Right? You might seem crazy, but guess what? There's nobody else around, so who cares? You start talking to the rubber duck like I am right now, and I'm saying, well, this is the thing I tried. This is what happened on line 23. This is what happened on line 24. And yeah, now I get what's wrong, right? Just by simply, putting or organizing it into your own words in order to communicate it is enough to understand 9 times out of 10 of what's wrong. Right? And that's rubber duck debugging. So even if you can't afford a nice debugger, you can at least afford a few words. Right? All right, then have a good weekend. Remember that your assignment 3 is due this Friday, so hopefully you've gotten a good start on it, and hopefully you're 90% done with it. Remember, midterm 1 week from today.